Alright, here are a couple more example limiting reactant problems and excess reactant problems. So, our question reads, a 50.6 gram sample of magnesium hydroxide is reacted with 45 grams of hydrochloric acid according to this reaction. So here are our two reactants, magnesium hydroxide and hydrochloric acid. The question is, what is the limiting reactant? Limiting reactant problems are always two stoichiometry problems in one, because we're given two lonely numbers. The first lonely number is 50.6 grams of magnesium hydroxide. So we have 50.6 grams of magnesium hydroxide. And our other lonely number is 45 grams of HCl. So we start a new one with 45 grams of HCl. Now the trick with limiting reactant problems is that this doesn't tell us what we're converting to. That's because you get to pick. You can convert either to magnesium chloride or water. But whichever one you pick, you have to convert both reactants to the same product. So I'm going to select water. The first thing we need to do is to balance the chemical reaction. So when I look at this chemical reaction, I see one magnesium on this side and one magnesium on this side. Balanced. Hydrogen and oxygen always come last, so next I see one chlorine on this side, two chlorines on this side, so I would put a 2 in front of HCl. Now when I look at this, we can now work with hydrogens and oxygens. I see that I have two hydrogens, because that 2 gets distributed, and two oxygens, because it gets distributed there. So that gives us 2 hydrogens on this side, plus 2 more hydrogens here for a total of 4 hydrogens. 2 hydrogens in front of our water. If we put a 2 in front, that's balanced. Now we also have 2 oxygens to match our 2 oxygens from over here. So now we have a balanced chemical equation. We'll just put 1s in front of magnesium chloride and magnesium hydroxide for housekeeping. So our coefficients are 1, 2, 1, 2. So now I've decided to go to water. So I'm going to convert both of my reactants to water. So the only way to cancel out grams of magnesium hydroxide is with grams of magnesium hydroxide. And then I can go to moles of magnesium hydroxide. When it's a grams to mole problem, it's always 1 mole. And for the grams, we have to figure out how much magnesium hydroxide weighs. If you look on the periodic table, magnesium's atomic weight is 24.3. We're going to add that to how much oxygen weighs, which is 16. But remember, we have 2 oxygens, so 16 times 2. We'll put that in parentheses. And then we also need to add the weight of 2 hydrogens. Hydrogen weighs 1 times 2. So we end up with 24.3 plus 32 plus 2. So 24 plus 32 is 56.3, plus 2 more is 58.3. So our magnesium hydroxide weighs 58.3 grams per mole. Now we need one more step. We need to get to moles of water in this case. First we need to cancel moles of magnesium hydroxide. Only one way to cancel moles of magnesium hydroxide. That's with moles of magnesium hydroxide. And then we can go to moles of water. Now, the numbers we use to populate these spaces come from our balanced chemical equation, because the mole-to-mole ratio always comes from the balanced chemical equation, and this is our mole-to-mole ratio. So moles of H2O looks like it's a 2, so we'll put a 2 out front. And moles of magnesium hydroxide looks like a 1, So we'll put a 1 out front. So now, to solve this problem, we take 50.6 times 1 times 2 divided by 58.3 divided by 1. And the answer we get will be in moles of H2O. And so when I do that multiplication and division, we end up with 1.74 moles. 3 significant figures in our answer because we had 3 significant figures in our lonely number. So our next problem, remember that all limiting reactant problems are really 2 problems in one. We have 45.0, it's important for significant figures, grams of HCl. And we do the math the exact same way. So I need to cancel out grams of HCl. Only one way to do that is with grams of HCl. And then I go to moles of HCl, because I can't jump to a different compound unless I'm at moles. Whenever it's grams to moles, it's always 1 mole. HCl, chlorine weighs 35.5, hydrogen weighs 1, so you add those together, and our HCl weighs 36.5. Open up one more set of parentheses. I need to cancel out my moles of HCl, so I'll have moles of HCl down below, and moles of H2O on top, because remember, if we pick H2O for the first problem, we must select H2O for the second problem. And our mole to mole ratio, in front of H2O there's still a 2, and in front of HCl there's a 2. So now we take 45 times 1 times 2 divided by 36.5 divided by 2. The 2's will actually cancel nicely, so it really just turns into 45 divided by 6.5. So now, when we do that, we come up with 1.23 moles of H2O. 3 significant figures, because we had 3 significant figures. Okay, so now we've identified which is the limiting reactant. Whichever one makes less moles is the limiting reactant. So we ran out of HCl first. So hydrochloric acid is our limiting reactant. If hydrochloric acid is our limiting reactant, that means that magnesium hydroxide must be our excess reactant. The way we figure out our excess reactant is just like this. We take the moles of H2O that we could make. Remember that this is the most H2O we could make, because then we'd run out of HCl and there wouldn't be any left. So we'll have magnesium hydroxide left over because it could have made more H2O. So when magnesium hydroxide and HCl react, all the HCl gets used up, but some magnesium hydroxide remains. We're going to calculate out how much magnesium hydroxide remains right now. This number of moles is our lonely number for the excess reactant problem. So we start with 1.23 moles of H2O. This will be a 2-step dimensional analysis problem. First thing we need to do is cancel out moles of H2O. And go to moles of HCl. Moles of MgOH2, the excess reactant. Because we want to figure out how much is left over, so we need to get to grams of magnesium hydroxide. So we'll go moles of magnesium hydroxide. Because this is the mole to mole ratio, we'll get these numbers from the balanced chemical equation. There's a 1 in front of magnesium hydroxide and a 2 in front of water. So a 1 in front of magnesium hydroxide and a 2 in front of water. Last step, we're going to cancel moles of magnesium hydroxide, and we're going to convert to grams of magnesium hydroxide. Always 1 mole when it's grams to moles. And fortunately, we calculated the mass of magnesium hydroxide up here as 58.3, so we can reuse that. Now, when we calculate all of this out, we'll take 1.23 times 58.3 divided by 2. And when I do the math, I get a number 35.9 grams of MgOH2. Okay, this is how much magnesium hydroxide was used to make that many moles of H2O. So if this is how much is used, and this is how much we started with, all we have to do is take this number and subtract it from what we started with. So, just to give you a visual, that 50.6, we subtract the number we've just found, which is 35.9, and we end up with 14.7 grams. So we had an extra 14.7 grams. So that's how much excess reactant we had. Okay, let's do one more of these problems. They take up a lot of space, so I'll try and space it a little better so that it looks a little cleaner. Next problem. Here we have sucrose combusting with oxygen to create carbon dioxide and water. First step is always to balance the chemical reaction. So I'm going to talk this one out. On this side I see 12 carbons. On this side I see only 1. So the way we balance that is putting a 12 out front there. Next I see 22 hydrogens on this side, only 2 on this side. The way we balance that out, 11 times 2 is 22, so that's balanced. Now we need to balance our oxygens. I see 11 oxygens here, plus 2 more is 13. And on this side we have 12 times 2 is 24 oxygens there, plus 12 times 2, plus 11 times 1 is 11. So that gives us 35 oxygens on this side. If I have 11 oxygens here, I don't really want to touch those because it messes with everything else. So if I already have 11, I need to figure out a way to make this equal 24 oxygens, so that the 11 plus 24 is the same 35 on this side. So the way I'll do that is by multiplying this oxygen by 12. So 1, 12, 12, 11 is my balanced chemical equation. So now the question becomes, if I have 10 grams of sucrose and 10 grams of oxygen, which is the limiting reactant? So we're given 2 lonely numbers. We'll use 2 lonely numbers. 10 grams of sucrose, which is the C12H22O11, and 10 grams of O2. And we're going to convert to figure out how much of each one gets used and how much product we can create. Remember, it's a limiting reactant problem, so we're not told what to convert to. You get to choose. I'm going to choose CO2 this time. Last time we picked H2O, this time I'm going to choose CO2. So we need to calculate out to CO2. This time I'm going to calculate out all the way to grams of each, because sometimes you may be asked how many grams of each substance you could make, or what's the most grams you could make, and that will be your limiting reactant. So we're going to go all the way to grams this time. So we're going to start off by canceling out our grams of sucrose. Grams. I'm just going to write sucrose as CHO. Just know the subscripts are still there. I'm just not going to write them to save some space and time. 2 moles of CHO. We have 1 mole, and now we need to do some math. So carbon weighs 12, and we have 12 carbons. So that's 144. Plus, hydrogen weighs 1, and we have 22, so plus 22. Oxygen weighs 16 times 11, so that's 176. So when we add all of those up, we'll get our mass. When you add all of those up, you should get 342. Remember that this is really this compound here. Alright, next we'll cancel out moles of sucrose. So I'll have moles of CHO. Remember that's C12, H22, O11. And now I can go to moles of CO2. I look at my balanced chemical equation and see that in front of sucrose I have a 1, so I'll put a 1. And in front of CO2 I have a 12, so I'll put a 12. One more parentheses. We'll cancel out moles of CO2 and go to grams of CO2. 1 mole of CO2 is equal to 44 grams. I know that because carbon weighs 12 plus oxygen weighs 16 times 2. 16 times 2 is 32. 32 plus 12 is 44. Okay, and that will give me grams of CO2. So now all I need to do is take 10 times 12 times 44 divided by 342. And that answer is 15.4 grams of CO2. Alright, now remember every limiting reactant problem is really 2 problems in one. So the next thing we need to do, just going to clear some space out here, is to do the same steps for converting grams of oxygen to grams of CO2. So the first thing we need to do is cancel out grams of oxygen and go to moles of oxygen. For every 1 mole of oxygen, it weighs 32 grams. Because each oxygen weighs 16 from the periodic table, 16 times 2 is 32. In the next step, we'll cancel out our moles of O2, and we'll convert to moles of CO2. And again, we'll look at our balanced chemical equation and see that in front of CO2 we have a 12, and in front of O2 we have a 12. So those will cancel nicely. Last step. The last step will look the same as above. We'll have 1 mole of CO2 and 44 grams of CO2. And so now all we need to do is take 10 times 12 times 44 divided by 32 divided by 12. But if I'm multiplying by 12 and dividing by 12, they'll just cancel out. 10 times 44 is 440, so I really just need 440 divided by 32. When I do that math, I get 13.8 grams of CO2. So if the question were to ask how much CO2 can be made, your answer would be 13.8 grams of CO2, because that's when you run out of limiting reactant. And the limiting reactant is the 10 grams of O2. Once you run out of that O2, this is as much CO2 as you can possibly make. And this starts our next problem. So if O2 is our limiting reactant, then sucrose is our excess reactant. And so we're going to convert from grams of CO2 to grams of sucrose so we can see how much we used and therefore how much we have left over. So we'll take that 13.8 grams of CO2 and we'll do a three-step dimensional analysis problem to get to grams of sucrose. So grams of CO2 on top, moles of CO2, grams of CO2 on the bottom, moles of CO2 on top. 1 mole for every 44 grams, found the same way as here. Carbon is 12, each oxygen is 16. 12 plus 32 is 44. Okay, next up, we'll cancel our moles of CO2. And we'll go to moles of sucrose, which is our C12H22O11. And in front of CO2, for our mole-to-mole ratio can only be found from the balanced chemical equation. So in front of CO2, we have a 12. In front of sucrose, we have a 1. Last step. We need to cancel out moles of sucrose. So C12H22O11. And go to grams of C12H22O11. And for every 1 mole of that, we calculated sucrose to weigh 342 grams. So now the problem becomes 13 times 342 divided by 44 divided by 12. Alright, and when we do those calculations, we come up with an answer of 8.94 grams. Oh. I don't know why I wrote 3.4. Excuse me. 8.94 grams of C12H22O11. So this is how much sucrose was used to make this much CO2. So the way we figure out how much we have left over is we take this number and subtract it from how much sucrose we started with. So we started with 10 grams of sucrose. From that 10 grams of sucrose, we'll subtract 8.94, and we will get 1.06 grams of sucrose left over. So 1.06 grams of sucrose remaining is our final answer. Thanks for watching. Come in if you have any questions.